So guys, here we are going to solve two problems related to wronskian, and this first problem I have taken from June 2016's paper. This problem, read this question carefully. It says that let y1 and y2 be two solutions of the problem. This is the differential equation given to you along with this condition y0 equals to 0, where a and b, these are real constants and w be the wronskian of y1 and y2, and simply they are asking for options on this wronskian or wt. Okay, so let's proceed further with this problem. So after that we will come to this second question. Okay, it is not a very hard problem, but you should be careful with your technique. So look at y double dash t plus a y dash t plus b yt equals to 0. You can immediately use the Abel's formula, which I have discussed in the previous video. You can have a look on that formula. Otherwise you can go by the manual process as well, okay, so that you will get the whole flavor of that Abel's formula. Okay, so this is the equation, and y1 and y2, these are two solutions of this equation. So immediately what you can do is, this equation will be satisfied by y1 and y2 individually. So you can write b y1t equals to 0 and y2 double dash t plus a y2 t plus b y2t equals to 0. Okay, now look at, these are the two equations you are getting after using that condition that the given y1 and y2, these are two solutions. So multiply this equation by y2 and this one by y1, then subtract. So what you are getting is y1 double dash y2 minus y2 double dash y1 plus a into y1 dash y2 minus y1 y2 dash equals to 0. So simply you are getting this one. Now look at, here w is the wronskian, so you want y1 y2 y1 dash y2 dash, so y1 y2 dash minus y1 dash y2, getting this one. So you can simply do the differentiation of w and you will get y1 y2 double dash minus y1 double dash y2, this expression. So we will use these two expressions here in this equation and we will get dw dx plus aw equals to 0, and that immediately implies a dx equals to 0, separation of variable, and this will ultimately lead, after integration we will get this stuff, and finally we have wx equals to k into e to the power minus ax. Okay, so this is the whole scenario. By using Abel's formula you can immediately get this expression, no problem with that as well. You can use that formulation as well. Okay, so we have wx equals to k into e to the power minus ax. Now we are going to use this condition y0 equals to 0. What do we mean by y0 equals to 0? Look at, this is yx is a solution, that means it involves two solutions, fundamental solution y1 and y2. Whenever y0 equals to 0, that immediately implies your y1 at 0 equals to 0 as well as y2 at 0 equals to 0, isn't it? Which immediately implies the corresponding wronskian, that means w0, it is also going to be 0. At x equal to 0, the wronskian, it is also 0, which implies from here you will get k into e to the power 0, means 1 equals to 0, that means k equals to 0, isn't it? So just resubstitute here and you will get Wx equals to 0 for all x belongs to R, because you have got this result for all x belongs to R. So finally this is your result, and now go to the options. Obviously first option says the exactly same thing what we have got. Fine, thus the first option is correct. Okay, and obvious fact is the second, third and fourth, these are all wrong options. You can have a look and it will be clear to you. It's nothing special, because second option it is constant, third option it also says that W is a non-constant positive function. Obvious fact, it is false. Fourth, it is also, because W, they are saying there exists T1 T2 belongs to R such that WT1 less than 0 less than WT2 and all these things, but you are getting W as 0.